Hello, everyone. My name is Jeff Cooper's Ghost. These are the two muzzle brakes that we will be installing on our client's AR-15s. They were supplied by the client. I want to talk a little bit about them, and I figured it would be a good time for a book review. This is The Accurate Muzzle Brake by Troy Newlon. I'll talk a little bit about the author. There's not much to say about him in here. I'll go over the contents and talk about who this book would be good for. If you never intend on making or manufacturing or building a muzzle brake in your life, this is still a very good resource to understand how they're made, why they're made, and why you would want one over the other. So it's a good reference for someone, just a basic consumer looking for some more information on helping them make a decision on muzzle brakes. Other than that, it is primarily, there goes the heater. Other than that, it's primarily marketed towards those in the gunsmithing industry who want to make money building muzzle brakes. So let's get right into it. That's our author, Troy Newlon, Newlon Precision, in Mariposa, California. Table of contents. We have muzzle brake design, how muzzle brakes work, hole pattern and hole diameter, accuracy, the exit hole, crowning the muzzle brake steels, accurizing the brake, indexing the brake, contouring the brake, rotational indexing, job setup, crown savers, gunsmithing, lathe and mills. Chapter 3, we go over building the brake, tooling setup, threading the brake, tapping on center, milling and drilling hole patterns. Chapter 4, we go over threading the barrel, turning the thread diameter, setup for threading, types of infeed, angular depth threading, calculating angular depth, thread inserts, thread fin classifications, thread dimensions, muzzle brake accessories, and a recoil chart on some common calibers. We also have the last chapter on making money, safety, conclusion, and resources on this thing. Let's read over the introduction. Historically, in America, the first muzzle brake to stand out was the Cutts compensator, designed by Colonel Richard M. Cutts in the early 1900s. It became famous when it was attached to the Tommy gun Thompson machine gun. All handheld, fully automatic machine guns suffered from uncontrollable recoil, rise, when fired in full auto. With a Cutts compensator installed, the muzzle rise was virtually eliminated, giving the shooter control of his weapon. Cutts compensator, subsequently adopted by U.S. military, used on many other guns, including Browning automatic rifle. It was very popular on shotguns through the 60s and still sold today. Even with this early popularity, the muzzle brake remained mainly a military application and only became to be popular with sporting shooters in the late 70s. We have learned a lot in the interim. By the way, this book, this is the second edition of the book, copyright 2012. I think it's 2007 over here, the original copyright. I don't know what edition they're on right now. We have learned a lot since then. In this book, I will share do's and don'ts of muzzle brake design and function. We will detail the machining process for building and installing muzzle brakes on sporting rifles. That's the difference here. We're going to be talking, our application here is a gas gun. But you guys will get an idea of how recoil is managed through these different designs as we get into this book. It is my sincere hope that by sharing my experience of more than 30 years of muzzle brake building, that it will help you build better, safer, and more accurate muzzle brakes. I hope you will find this book of value to both the skilled gunsmith and the beginner. The reader who applies this information in a machine shop setting should have basic machine skills and be qualified to safely operate a lathe and mill. Reader assumes all risk. liability. How do muzzle brakes work? Muzzle brakes work by redirecting the rapidly expanding gas caused by burning powder. It is possible to redirect as much as 90% of these gases. Now keep in mind that with a gas gun, these numbers are going to fluctuate some because we are diverting gas from the cartridge from the cartridge burning in the barrel through the gas port. When I asked Chad Albrecht, School of the American Rifle, how muzzle brakes can affect function on a gas gun, he said they can. However, how they do is a much different answer depending on your gun, depending on your gas port diameter, the efficiency of your carrier group, and how your parts play together. There's no defining answer on how a muzzle brake is going to affect the gas efficiency and cycling and reliability of your AR without testing it. So when we put these on, we will be testing without the muzzle brakes, and we will test with the muzzle brakes on. It is possible to redirect as much as 90% of these gases, leaving only the weight of the bullet to affect the remaining recoil. The recoil is changed, producing a rearward push, greatly reducing muzzle jump and the snap and jab, which we all know can take the fun out of shooting. This is simple physics. Newton's law: for every action there is an equal and opposite reaction. With most of the gases redirected, the next factor is the weight of the bullet. For example, 22-250, 50-grain bullet would have a much greater percentage of recoil reduction because of the small bullet weight and large powder capacity. Compare this to a 30-06 with a 180-grain bullet. Powder to bullet ratio would change dramatically. And now it is the weight of the bullet that is producing the recoil. With most muzzle brakes, one can expect a recoil reduction of 40 to 50% depending on the cartridge. Whether you're shooting varmints with 22-250 and want to see impact through a 12x scope, or big game hunting with a Magnum, muzzle brakes will allow you to get a second shot off faster and concentrate on your target, not the rifle's recoil. So, these next few pages are going to get into some the designs that you will see throughout the industry. Muzzle brake design. In this chapter, we will discuss some of today's popular muzzle brake designs and how they work. By understanding design and function, you will be able to choose and build the best design for your application. There are many factors that affect muzzle brake design, and not all of them have to do with how they function. Many people like the look of a clean muzzle brake turned to the barrel diameter. But what price is paid for looks? How is muzzle brake design a give and take proposition? We will answer all these questions and more in this chapter. First, we'll start by giving you some simple rules. Build it safe, build it accurate, port as much gas as possible, build it as efficient as possible, build all hole patterns symmetrical. And he stresses this throughout the book. If you want the accurate muzzle brake, your hole pattern must be symmetrical. So these next few pages are going to go over some of the designs and combinations of designs that you will see in the industry. The standard design. While studying these muzzle brake designs, keep in mind that it is possible to mix and match designs and hole patterns to build more efficient muzzle brakes. Many muzzle brake manufacturers are known by their particular designs and have patents, so take care not to infringe on any patent rights. In our first design, as in all others, look for the arrow flow of efficiency. The more efficient the muzzle brake design, the greater the reduction in recoil and muzzle rise. This is the standard brake, one of the most common and simple brakes to make. This is what we didn't design. This is what we manufactured in one of our machine shop projects at Colorado School of Trades. Very similar to this. This is the standard brakes. One of the most common and simple brakes to build. Consists of a single open chamber to the first set of holes. In this design, as in most others, the first set of holes will port the majority of gas. followed by several other baffles or chambers. When drilling the inside thread diameter of this break, it helps to leave the drill angle at the first set of holes. And what he's talking about is this is obviously an undersized drill bit, but you can see the cone that a standard drill bit leaves, and that cone in the first baffle there is what they're talking about. When drilling the inside thread diameter of this break, it helps to leave the drill angle at the first set of holes. This helps utilize the remaining baffles by directing gas to the next chamber. Many different hole patterns and sizes can be used with this design. It is a good all-around muzzle brake, but lacks the efficiency of some more complex muzzle brake designs. If you watch a lot of School of the American Rifle, we use the word, Chad uses the word efficiency a lot. Remember, we're going to use the word efficiency as we go through these designs. This is about all of that gas going into the muzzle brake and being diverted from there. When we talk about efficiency in the gas gun, we're talking about how good of a seal there is between that 3-bore dimensions on the carrier to seal off that gas, or how loose those tolerances are to allow gas to pass through it. Pros of this muzzle brake: average gas porting efficiency, an average degree of machining difficulty in manufacturing. Cons: not as efficient as more complex designs. Let's move on to the next one. This is the 7-degree brake. You can see very similar to the one we just went over. However, these ports are angled 7 degrees. Different manufacturers angle their holes at different degrees and in different hole patterns. They do this to move sound and muzzle blast away from the shooter, giving some small degree of relief. Muzzle brake design is a give and take process. We know Newton's third law of motion: every reaction, opposite reaction. In terms of muzzle brake design, this means that when the holes are angled forward too much, reduction in recoil will be lost. How much is too much? The consensus of opinions among gunsmith and muzzle brake manufacturers seems to be that anything greater than 7 degrees is unwarranted. 7 degrees is enough to direct gas forward, but is not so much to adversely affect recoil reduction. For maximum recoil reduction, one would do just the opposite: face the holes rearward. This appears on military applications like tanks and howitzers, and some non-military 50 caliber rifles. So why don't we all have this type of brake with the holes ported rearward on our deer rifle? Because directing the muzzle blast back at oneself or one's hunting partner isn't pleasant. In this case of give and take, we give up maximum recoil reduction for civility. Even with this civility, some shooters will never own a muzzle brake because for them the benefit of recoil reduction does not outweigh the discomfort of the muzzle brake. When machining, holes must be cut with an end mill or a mill drill. Standard drills do not cut well at angles and tend to walk on the surface, especially on circumferences. What he's talking about is obviously again, size difference here. The milling cutter tends to be way more rigid and stable than the drill bit, which has the angled head. Tends to walk very easily on when cutting something. This is a gauge, don't do this to your gauges, on a circumference or round surface. What are the pros on this one? Average gas porting efficiency, some noise reduction felt by the shooter, not as efficient as other complex designs, greater degree of machining and manufacturing difficulty. Here's the next one, the choke chamber design. The choke chamber design utilizes one single chamber and is probably one of the simplest and oldest designs. The cuts compensator, that we talked about earlier, is a choke chamber design. This large, full choke chamber compensator for shotguns and rifle has a very distinct sound when fired. The same full open choke chamber principle applies here. This design is also simple to machine and manufacture. It has one large wall for deflecting gas to create back pressure, which forces the gas to escape through all the holes. Increasing the efficiency of the break. The flat wall at the end of the chamber is very critical for efficiency. If the hole is drilled to the depth of the break, the angle of the drill will create a cone which will direct gas out the end of the break. This will greatly reduce the efficiency of the muzzle brake. The cone at the exit hole can easily be squared using a 3-flute 60-degree high helix end mill or a boring bar. Small design details such as this make a big difference in recoil. Again, same thing here. We're talking about the drill angle at the exit here. This cone at the end of the design should be flat. So your drill goes in like yo, stops right there, and leaves that angle. You go in there with a flat end mill and square that surface. Or boring bar, as they say. Very good gas porting efficiency, average degree of machining difficulty, not as efficient as some other complex designs. We're getting into the complex design here. This design, we will discuss another fundamental law of physics, the path of least resistance. In physics, the path of least resistance is always taken by objects moving through a system. For example, water flowing downhill flows along the path of least resistance as it is pulled downhill by gravity. In muzzle brake terms, this means the first set of holes or ports will release more gas than the second and third, etc. Rapidly expanding gas flows the path of least resistance to its first opportunity of escape. That sounds like it should say follows the path of least resistance. In this design, each hole or port has a step or wall to deflect the gas and redirect it outward. Maybe you can't, let's zoom in on that. Maybe you can't tell just from looking right away, but these steps are smaller as they get towards the muzzle. You see that first chamber is larger here than it is here and here. This is an attempt to enhance and redirect the path utilizing the entire hole pattern. There are different versions, combinations of this design. One example is the step chamber with 7 degrees angled forward. Other examples include a multitude of different hole patterns, as well as milled ports and slots. The machining accuracy of the steps and location of the holes has to be perfect. Each hole and or port has to be in front of each wall. The walls serve to redirect the gas out of the holes. When built correctly, this design results in one of the most efficient muzzle brake designs. Very efficient gas porting, greater degree of difficulty to machine, and hole placement accuracy required for manufacturing. We have a couple more to go over. This is the linear compensator design. This is a very popular muzzle brake design. It is unique in the fact that it directs gas forward as well as to the sides. The maze of holes, slows the rapidly expanding gases as they are departing the muzzle brake. This method of slowing the gases is the same method used on sound suppressors. You're going to see some similar concepts about sound suppressors as we get into more of these designs. It also is used on other military applications such as compensators, which is the military's version of a muzzle brake. The military term for this design is linear compensator. On smaller diameters, the brake cannot be turned down due to the linear holes. This is not a problem unless you want a very slim muzzle brake. So what we have here is a combination of linear and milled side ports. Milled angled side ports. You can see the back angle cut into these things on the side, and it's got that S-shaped pattern to them. In fact, the larger the area of the vertical holes on the brake, the more the gas is deflected. In fact, the larger the area of the vertical holes in the brake, the more the gas is deflected. The more deflection, the greater of accuracy in the brake. Reducing the wall thickness too much will result in loss of efficiency and can jeopardize safety. So, you guys can see here there is some substantial amount of meat or material around these holes. That it has to be that way for safety. As for machining, this design takes more steps to build and has a higher degree of machining difficulty. The side holes or ports must be in perfect alignment with the linear holes. So these must be perpendicular to each other. The linear holes and the angled side cuts. Efficient gas porting, some noise reduction for the shooter are the pros for this one. Greater degree of machining difficulty and hole placement accuracy required for manufacturing. The diameter of these cannot be turned down slim. Those are the cons. Okay, this is the cone design. One of the most complex. This may very well be the ultimate design in muzzle brake efficiency. The cone literally strips the gases away from the bullet as it passes through the brake. Why then does not every muzzle brake manufacturer offer cone-type muzzle brakes? There are several reasons. The first is erosion, sometimes called brake burn. All brakes are subject to erosion from the hot burning gases. The leading edge of the cone would be very thin on small diameter brakes. The thinner the steel, the faster it erodes. The muzzle brake should last at least as long as the life of the barrel. There are some heat-resistant materials that could be used, such as ceramics and exotic alloys, for example, Inconel and Hastalloy, but these are very hard to machine and are very expensive. Another possible reason why cone brakes are not common is that a cone is too long. A cone that is too long may hurt accuracy. There are some independent studies that say an exit hole longer than 1/4 of an inch, 250 thousandths, causes loss in accuracy. An 11-degree crown would help shorten the exit hole length. Also, it would be very difficult to machine inside a small diameter brake. The machining process would therefore have to be done in 2 pieces. This would involve the cone being built separately, assembled, then machined for concentricity. Concentricity is the utmost importance in any muzzle brake design for accuracy and safety. Large military-type cone brakes are fabricated in multiple pieces, welded together, and final assembly for concentricity. Sound something similar to suppressor designs. There have been cone muzzle brakes manufactured for small diameter barrels and varmint target barrels. The simplest and best design I have seen was a 2-piece welded brake. It was very well made and simple in the fact that it used 1/8 inch flat washer to fabricate the cone. Washer was pressed into a cone form, then welded in place. Washer could easily be pressed into the cone form die with a cone form with a die, and this could be done on any shop press at very little expense. Designer used what looked like a heavy wall tubing for the body. The difficulty of manufacturing this type of two-piece brakes lies in the quality of the weld. The weld looked so good that it must have been made with an automated welding machine. It was a very fine bead, probably TIG welded. The weld ran around the outside edge of the washer on the face of the brake. It would be very hard to do this in an average small shop, welding one at a time. One would have to spend considerable amount of money on automation, or send it to a shop to have it with the right equipment, had it made with the right equipment. For safety, the welding process would have to be tested for its failure rate. There could be no allowance for failure. If the washer came off under fire, it would fly anywhere and possibly injure and kill somebody. There's a tremendous amount of liability involved in making these things, you guys. It's something to really consider if you're making them for somebody else. Again, this type of two-piece brake would have to be assembled and machined for concentricity. The exit hole in the washer would need to be smaller than the smallest caliber so that it could be trued during the final machining process. Machining tubing instead of bar stock always saves time, though not necessarily money. There is a lot less material to be machined and removed. However, tubing can be much more expensive than solid bar stock. If one had the right equipment for the job, this design, utilizing a washer and tubing, would be a good candidate for mass production. So you can see here the design of what we're talking about. We've got our ports leading up in our brake, leading up to the 7-degree angle in front here. Notice this is the opposite of the drill angle and our choke chamber design here. Instead of the angle going this way inside of the design, which we want to get rid of, this utilizes that angle back in reverse to push that gas out to the last port, instead of that gas being forced forward by the inverse of that cone there. I hope that makes sense to you guys. So this is very efficient gas porting. Requires a greater degree of machining, must be built in two pieces. That's there's more to this book than just the designs, but that's about it. We will let's go over this last page here. This is just a sample of muzzle brake design. There are many other designs that can be made combining all of these samples. For example, our last design, the cone brake, could incorporate a hole pattern of 7 degrees forward, offering very efficient brake with some noise reduction. Better yet, come up with a new and better design that no one has thought of. It might be hard, but not impossible. This was written, of course, over 10 years ago, so who knows what's out there now. Hole, pattern, and diameter. This is the last section we'll go over. Please do not sue me, Mr. Newlon. Large hole or small hole muzzle brake design can be summed up very easily. If the area of a large 24 hole pattern brake is the same of the area of a small 48 hole pattern brake, the area is the same. They will port the same amount of gases. This being said, it does not hold true when slots or oversized holes are incorporated into the design. Sound familiar? How about something like this? Oversized holes on the side like this? The hole area may be the same as a brake. Where did I stop here? The whole area may be the same as a brake with a 48 hole pattern, but the milled slots create large flats on the inside that deflect the gas more efficiently, therefore porting more gas out of the same area of holes. Why are not all muzzle brakes built this way? That aesthetics issue. The military look of the large brake with large ports is not for everyone. Looks aside, these types of brakes can be very efficient when built correctly. When building this type of brake, resist the urge to drill holes on the top unless you are willing to drill them on the bottom. It has to be symmetrical to be accurate. Hole diameter can affect safety. It is a very real concern. If these holes are too large or the pattern is too close together, the muzzle brake can fail from metal fatigue. This type of failure could seriously injure or kill somebody. Your design should be well tested before it is released to the public. How large is too large? How close is too close? A good rule to follow is to have at least as much distance between the holes as the hole diameter. For example, a brake with 250 quarter-inch holes and a pattern that is spaced quarter-inch apart would have as much area for strength as it had for porting gas. The surface area between the holes of the steel will increase with the diameter of the hole of the brake and is less critical on large brakes. So with that being said, we have the combination of a linear compensator, angled side ports, and one with a large milled ports on the side of it. Other than that, everything else in this book is about the manufacturing process. He's got information on work holding and setups in here, doing the math on figuring out these depths of threads. He's got setups in the mill, or the lathe, calculating the angular depth and showing the process for cutting threads. Good information. Even if you're cutting threads for attaching a barrel to an action, it's a good source of information on the thread cutting process. So again, if you're in the business, if you are a gunsmith manufacturing brakes or even working on brakes, or guns that could possibly have brakes, you never know what you're going to run into, what someone's going to bring you. This is a good source of understanding what's going on with the muzzle brake design, and shows you things to look for safety and potential accuracy loss. That's it, you guys. Troy Newlon, the accurate muzzle brake. I would say it is definitely required reading. Thanks for watching, guys. Thanks for the likes and the subs. We'll get these things back together and move on with our AR test firing.